Let's continue talking about weighted voting. That's what we started talking about last time. Weighted voting. I will refresh your memory. The way it works is you have typically a small number of voters, and they each have different weights. So each voter has a weight. These weighted voting, at least as far as we're going to talk about it, is only used to decide sort of yes or no questions or things between only two alternatives. That's the only setting in which we're going to discuss weighted voting. Each voter has a weight, which represents kind of how many votes they get. Like I said last time, this is basically the system that we use for the Electoral College to elect the president. But this kind of thing happens in the real world all the time when you have people who are assigned different weights in voting. This is the typical scenario in, say, corporations which are owned by different people in different weights. You know, especially of a publicly traded company that has, shareholders who own this much percentage of the company, they get that much weight whenever the company has to vote about something. So this happens all the time in the real world. Anyway, each voter has a weight, and then there is a quota that you have to get to in order to sort of make a decision. We think of these as sort of like yes or no questions, and in order to get to a yes, there have to be enough votes to meet the quota, all right? There's a quota to be met. All right, and the way that we write these down, so a typical example, I have to tell you how many voters there are, what are each of their weights, and then what's the quota that they need to meet in order to actually do anything, pass the vote or something. So let's say we have, here's just a simple example. Let's say we have 4 voters, and the weights are 10, 10, 10, and 9. So there's 3 people with 10 votes and 1 with 9 votes. And let's say the quota is 30, all right? This whole scenario, usually I'm not going to write it in words like that. This whole scenario is written like we have sort of a very compact notation. You put the quota there, and then you put the various weights, and I'm always going to write them in order, biggest to smallest. All right. So that thing there with the 30, the colon, the brackets, that refers to a scenario with the quota of 30. 3 voters with weight 10 and 1 with weight 9. All right. And this is actually a good example to illustrate the basic point that I was trying to convince you of last time, is that when you just look at the weights, they can sometimes be misleading concerning the question about who has the most power. It is a fact that the 3 people with weight 10, they all have equal power because their weight is 10. It might seem like the person with 9 has only slightly less. The 3 10s are sort of equal, and the 9 is a little bit less. Actually, that's not true. In this particular example, the 9 has no power at all. This is the kind of thing that I want to think about, as we talk about the weighted voting systems. How exactly should we analyze this? So here, the 9 has actually no power to influence the outcome. You can see in this particular example, the only way to get to 30 is if all the 10s all agree. And in that case, you don't need the 9 for anything. And if all the 10s don't agree, then the 9 is not enough to reach the 30. So there is no scenario in which the 9 actually makes a difference in this particular setting here. All right? So even though by the numbers it looks like the 9 is only slightly less powerful, actually they are completely less powerful. They have no power at all. The 10s are all equal. The 9 is basically a nobody in this system. All right, this is the kind of thing that we want to try to analyze. this one you just kind of look at it and you think for a while and you realize the 9 doesn't matter. But is there some kind of a more, structured or more sort of routine way that we could sort of look at these numbers, maybe do some simple math to figure out actually how powerful are these people? All right, that's the kind of thing that we're going to look at eventually. Before we get into that, I want to talk about some practical restrictions. Some restrictions on the weights. There are many, I wrote these numbers down because I thought this would be an interesting example. And, as we go on, I'm going to be making up more and more examples. There are many ways you could make up examples that actually don't make any sense in the real world, or that you would never actually encounter in the real world. So here's an example of a system which you can write it down, but actually this is not a realistic system that would ever occur in the real world. Can anybody say what's unrealistic about this? Yeah.
None of the numbers equal 20.
Yeah, the numbers, what this means is the quota is 20. You have to get up to 20 in order for the vote to succeed. And we have 3 voters of weight 1 each. The problem is those 3 voters, they can't possibly add up to the quota anyway. So it's impossible for the quota to be met here. So in this case, the quota, which I'm going to write as Q, that's the Q, right? Q is too big in this case. It doesn't really make sense. I mean, you could imagine this, but this system would never be useful for anything in the real world. A system where the weights of all the voters are not sufficient to actually vote about anything. All right? So this is what I mean by some restrictions on the weights. That one right there doesn't make any sense. If the weights are, if I call them like W1, W2, W3, etc., first, I'm going to talk about 2 restrictions. The first restriction is those W's, they have to actually add up to something which is more than the quota, or possibly equal to the quota, right? It doesn't make sense if when you add them all up, you get something less than the quota. So we will require, I'm going to write this in it's not too fancy. Q has to be less than or equal to the sum of all of these things. Let's say they go up to the last one, maybe I'll call Wn. Say there's n voters, all right? I hope you remember your inequality signs, which way it goes. The thing on the left of that one is less, all right? So Q must be less than or equal to, I'm just writing in words what that means. Q must be less than or equal to the total sum of weights. Otherwise, you're never going to meet the quota, and that's a useless, that's an unrealistic scenario. All right? All right. Anybody got any pro tips on how to remember which one this means? I know this is confusing. I remember when I was a kid, I had a hard time remembering which one. And then one of my teachers told me, this when you see this way, this is like 4 is less than 10. And you can remember that because this is like the alligator, the teeth of the alligator. Remember that thing? I don't know. Yes, the alligator eats the bigger one, right? And my teacher also told me this. This is like the mouse, and the mouse eats the smaller one. How do you like that? But this actually, I don't know if you like that. This actually confused me even more, because then I find myself wondering, like when it says this, how do I know if it's the mouse or the alligator? The answer is it's kind of both. It doesn't matter. But I found that confusing. Is that did I just confuse you more? I don't know. Remember the mouse or the alligator. Or just remember. The pointy side is the smaller one, and the bigger side is the bigger one. Okay. I have since figured it out. I'm pretty confident in my mouse and alligator skills by now. Okay, so that's the first restriction. The quota cannot be too big, right? It has to always be less than this, which is what you get when you add up all the weights. Okay? It's also, this is a little bit less obvious, but it's also, there is also an unrealistic scenario if the quota is too small. So check this out. Here's another one which is unrealistic. So this is an example in which the quota is too small. Now, you might say, well, there's nothing really wrong with that. If the quota is too small, it just means that the vote will, it's easy for the vote to succeed. And that's, I mean, that's not necessarily a bad thing in the real world, isn't it? Actually, it is a bad thing. So this one here, I'm going to say the quota is too small. And the reason why you really don't want that, I would have you notice, in this case, you can meet the quota with only, for instance, using that 4, right? We can meet the quota if the 4 is in favor of the vote, right? If the 4 votes for whatever it is, but all the others are opposed, but the 5, and the 1 are against, right? And this is the unrealistic thing. Here you have the quota is being met even though a majority of the weights are against, right? Here you have 4 in favor and 11 against. But because the quota is so low, it passes. That doesn't make any sense in the real world. You wouldn't actually want to use a system like this. So here, a majority is against. And you don't actually want a system in which a majority can be opposed, but you still end up meeting the quota. All right. So the rule about this is the quota cannot be too small. And how small is too small? It can't be less than half of the total sum of the weights, because then you could have a majority that are opposed, but you're still meeting the quota. So here, the quota was too small, right? It must at least equal, let me say, it must at least be half of the weight sum. This is to avoid a majority being opposed, even though the quota is still met. All right, it has to be at least half of the weight sum. At least, meaning the quota has to be bigger or equal, actually straight up bigger than half of the weight sum. So that we would write it this way: the quota is greater than half of this sum of the weights. All right. Because if the quota is less than half, then that means you can actually pass the vote even if a majority is opposed, which doesn't make sense. All right. So those are the two restrictions about the quota. So you cannot, like I said, I'm going to be making up examples a lot as we go forward. You can't just make up anything though, because the quota has to be within this range, right? We said up here it has to be less than this thing. And then what I just said is it has to be greater than this other thing. So actually there's sort of a, we must have Q, I could write this as Q is like in between. 1/2 of the weights has to be less than Q, and that has to be less than or equal to all the weights. All right? So the Q is always kind of in between. I hope you don't mind me putting those two inequalities. That means the Q is in between those two numbers. And the one on the far left is the smallest. The one on the far right is the biggest. All right? This is just some technicalities about what sort of weighted voting systems are realistic. Basically, anything which does have this property, as long as the Q is in between the total sum and half of the sum, then that is a realistic situation that you might actually encounter in the real world. All right. Anyway, I think we can get on to my real sort of questions that I want to talk about. Sort of, I will, under the heading here, let's talk about maybe basics of power measuring. The big question is, can you figure out, just by looking at those numbers, who's got the real power in the system and who is powerless in the system, all right? And we want some kind of some kind of systematic way of doing this. Here's an example. This is one in which there's some obvious power relationship going on here. The quota is 10, and the votes go 12, 4, 2, and 3. Could anybody maybe describe who has the power here? And who doesn't? What do you say?
12.
The 12, yeah. Is it like the 12 has most of the power and the others have a little bit less? Sorry, I wrote them out of order. I always say I'm going to write them in order. I don't know why. It doesn't really matter, but. What about the 4, 3, 2? Do they have a little bit less power? No power at all? I think the answer is no power at all. In this case, you can see actually this guy, the 12, is capable of meeting the quota all by themselves, right? That means this 12 is going to decide the whole thing, and nobody else matters, right? If the 12 is in favor, the quota is met. If the 12 is not in favor, everybody else is not capable of adding up to the quota. So in this case, the 12 has all the power. And there's a name for that. We say the 12 is a, anyone want to guess the name? This is a word that we've used before in the context of voting, where one person has all the power. Dictator, yeah. You stopped after the first syllable. You could say that too, I guess. Dictator, right? Yeah, in this case we say that 12 is a dictator. And actually, it's very easy when you just look at the numbers to tell if someone is a dictator. Someone is a dictator when their weight is bigger than the quota or equal to the quota. And that's all you have to look for. So we say that 12 is a dictator. A dictator is very easy to identify. Anyone with a weight greater than or equal to the quota. So if you see one of those numbers over here is bigger than the quota or equal to the quota, then automatically that person is a dictator, which means they have all the power, and everybody else has no power at all. And there's actually a name for that, somebody with no power at all. So when one of them is a dictator, then automatically everybody else has zero influence on the outcome. So one of them is a dictator. The others automatically have no power at all. Now you might wonder, is it possible that two of them could be dictators? Like, is it possible that two of them over here would have a weight that's bigger than the quota? Actually, that is not allowed because of the rules about how big the quota can be. The quota, remember, has to be at least half of the total sum of the weights. And because of that, it's not possible for two of the voters to have their weights exceeding the quota. Anyway, when one of them is a dictator, the others have no power at all. And there's a name for that too. I will write this. If some voter has no ability to influence the outcome, they might actually have like a weight. You might see they have this many, they have a number, it's not zero, but it may be still that they have no ability to influence the outcome. No ability to influence the outcome. They are called, I'm not making this up, this is the word that they really use for this, a dummy. All right? This is a person who has no power at all in the system. Even if this doesn't mean their weight is zero. For example, in this example that I said at the beginning, 30, 10, 10, 10, 9. The 9 is a dummy in this case. All right? Even though the 10s are not dictators, but it is a fact that you need all three 10s to reach the quota. And actually, there is no scenario in which that 9 can affect the outcome either way, right? The power here is entirely held by the 10s. The 9 has no power at all. So here, this 9 is a dummy. But being a dummy is harder to identify than being a dictator, right? Dictator, you can just look for who's got more than the quota. But being a dummy is not so obvious. You have to kind of look at all these numbers and think about what are all the possible ways these numbers could add up to 30, and you will realize that the 9 is never part of that. The 9 is never relevant for those numbers adding up to 30. All right? Unless it goes way above, you could add them all up, you get to 39, but then you didn't need the 9 anyway. So that's the way you got to think about that. All right, so dictators and dummies, those are very basic measurements of power. There's one other kind of simple one, which is a little bit more subtle. How about this? Here's another example. Let's look at 12 is the quota. And then I got 9, 5, 4, 2. All right. So in this example, first of all, there's no dictator because none of the weights are bigger than the quota. So that's always easy to tell. No dictator. But I will have you notice, if you look at the numbers and think about all the ways that those numbers could add up to be more than 12, I think you will realize that the 9 here must be part of it if it's going to add up to 12. You cannot make 12 unless you use the 9, right? Because everybody else altogether only adds up to 11, right? 5 plus 4 plus 2, they add up to 11. The only way you're going to get to 12 is with the 9. Now, the 9 is not a dictator because the 9 can't make it to 12 all by themselves, but they are necessary in order to meet the 12. All right, so I'm going to say no dictator, but in order to meet the quota, we must use the 9, right? You can tell this by just adding up all the other numbers together, and you will see if I do 5 plus 4 plus 2, that's not enough to meet the quota. That means you have to have the 9 included if you actually want to get to the quota. And there's a word for this, and this is a word that is used in real-world politics. We must use the 9. So here we say the 9 there has veto power. All right. This means that this voter in the system, they are not capable of passing the vote all by themselves, but if they're not on board with it, it's not going to happen, right? That's the idea behind the veto power. So they have the ability to prevent it from happening, even though they can't actually make it happen all by themselves, all right? We say the 9 has veto power. So the vote cannot succeed. I'm just saying again in little different words. The vote cannot succeed without agreement from the 9. Right? That's why it's called veto power. All right. And these are the 3 kind of basic ways to look at power. The dictators, the dummies, and the veto power. It's very easy to tell who is a dictator. The dummies and the veto power, you got to look a little bit more carefully. But I want to do a bunch of examples. How about... Any questions about those so far? Yes?
So the example we just did, is there a dummy in that one?
This is a good question. Are there any dummies in this one here? You have to kind of look carefully. I think maybe the 2 is a dummy. It's not even obvious even when I say that if you should agree with me or not. What you have to think of is what are all the different ways that these 4 numbers could add up to 12. I think if you ever get past 12, the 2 was not actually necessary. Like for instance, these ones, if you're using the 2, you can't add these up to 13, which would be a scenario where the 2 really was important. If you left the 2 out, then it wouldn't have made it. So yeah, I think the 2 is a dummy here. But even that is not easy to see. And this is why, we're going to talk a little bit more about how do you identify dummies and such. But thanks for the question. Let's just do some other examples. How about this one that I mentioned a few times? I want to know, is there a dictator? Are there any dummies? And does anybody have veto power? So we already said, in this example, there is no dictator because none of those weights is bigger than the quota. So this has no dictator. Any dummies here? don't mean you all.
9.
Yes, the 9. Right. The 9 is a dummy. Great. That's because there is no way to add up these numbers to more than 30 in a way which actually uses the 9, right? The only way to get to 30 is by including the 3 10s. Then you get to 30. If you also throw the 9 in, it doesn't matter. And if you don't throw in one of the 10s, then you can't make it to 30. So the 9 is a dummy. All right. What about veto power? Does any of these voters have veto power? That means if you want to get to the quota, it is necessary to include one or the other of them. Yeah.
All of the 10s have veto power?
Yeah, each of the 10s, they all have veto power in this case because in order to get to the 30, you need each of the 10s. So no dictator, 9 is a dummy, and each of the 10s has veto power. Great. All right. Any thoughts about that? All right, let's just try a few more. I got another one, and then I have some for you all to try. I'll write the numbers. You tell me. How about this? The same, but I just threw in another 10. All right? How does that change anything? Does it change anything? Okay, is there, this time, is there a dictator? No. Remember, dictator is just somebody whose weight is already equal to or greater than the quota, which is not. So no dictator. Any dummy here? To me, I think the 9 is still a dummy, right? It is still true that that 9 cannot impact the results of the vote. So 9 is still a dummy. Any veto power this time? Last time it was a fact that you need each of these 10s are necessary to get to the 30. Is it still true? I think it's not still true because in this case, like this first 10 is not necessary to meet the 30 because the other 3 10s can add up to the 30. So actually, in this example, there's no dictator, 9 is a dummy, and no veto power. All right? Because each one of those 10s by themselves is not necessary to meet the 30. Because the other 3 10s can meet it without their help. All right? Excellent. I would like you to look at a few more examples and tell me, in each one, is there a dictator? Is there a dummy? Or there can be more than one dummy. And is there anybody with veto power? Again, there can be more than one of those. So how about you try these? Tell me each time if there is a dictator, a dummy, a veto power. I just got several examples here. See what you think. I'm going to walk around and see how you're doing, as usual. All right. Sorry, I just realized my first one here is violating one of those rules. Can I change that 9? It doesn't really matter, but let's make it a 3 instead. The quota there was too small. All right, talk to your friends if you want, if they're still talking to you. Yeah, the dictator automatically. Okay. Okay. Yeah. Alright. Okay. Alright.
I think it's because like your body's
Yeah.
so if you don't need it to get right. But then like I guess you could use the 2 instead of 3 for this one, so I don't think it's a dummy.
Yeah, but you could also say,
Oh, you could like this one is dummy. It's like
yeah, I mean,
you just need like you either need 7 or 1.
Yes.
Is it possible for one of them to not have a double one? Or do they all have?
Yeah.
Yeah.
Hmm?
And
Yes.
also, is just the veto power just the one that would like equal the quota, or how do you define that? 'Cause I'm not sure.
Yeah, it means that they are necessary to get to the quota.
Okay.
Like in the second one there, did you say anything about? Yeah, you said 5 has veto power.
Yeah, I said 5.
So when, and sort of a numerical way to see that is if you were to add the other 3 together, 4, 3, 2, that only adds up to 9, which is not enough. So you need the 5.
Okay. Thank you.
You guys doing good?
Yeah.
All right. All right, let's talk about these. These can be a little tricky, but it looks like people are feeling good about these. So in the first one, the 14 is a dictator. That's the easiest thing to identify. It's just if they exceed the quota or equal the quota by themselves, then it's a dictator. And in a scenario which has a dictator, automatically everybody else is a dummy, right? And some people ask me, isn't a dictator automatically have veto power? And the answer is yes. Veto power, remember, means that person is necessary to meet the quota, and that is always true. So here the 14 has veto power. Although that's kind of, I mean, once you say they're a dictator, usually we don't also say, yeah, it's true, they also have veto power. All right, how about the next one? There's no dictator here because none of those numbers is equal or greater than 10. So no dictator, no dict. What about veto power? You have to ask yourself, can any of these, is any of these numbers necessary in order to meet the 10? I think the answer is yes. I see some nodding heads. It's the 5 in this case. You might, if you're looking for veto power, you might as well start by looking at the biggest number here, and then see if I add together all the other numbers, can they meet the quota without the 5? And the answer is no, they can't. Here, 4 and 3 and 2 adds up to 9, which is not enough. So that means the 5 does have veto power. It might be natural to ask, okay, does the 4 also have veto power? It's possible to have more than one person with a veto power. The way to figure that out is, without the 4, I would add everybody else up and see if they can make it. But actually, they can make it. In this example, the 5 and the 3 and the 2, they can add up to 10. And so that means the 4 does not have veto power. It is possible to get to the 10 without the 4. Is there any dummy here? For those, you should start by looking at the, at the weakest ones and see, is there any scenario in which the 2 could actually contribute to making the quota? And actually, in this case, there is such a thing. I think I said this wrong to somebody as I was walking around. The 2 here is not a dummy because you can add up to 10 using the 2 by 5 plus 3 plus 2, right? That makes 10. So here, no dictator, the 5 has veto power, no dummy. No dummies, all right? It's a little tricky. You gotta look at, you sort of have to consider all possible ways to add these numbers together. It's a little tricky. All right, let's talk about this next one here. What do you say? Is there a dictator? Give me the thumbs. Thumbs down. Yeah, no dictator. That's the easy one. Anybody have veto power? Yeah, the 7. I mean, you should naturally consider the big ones here and see if they have veto power. The 7 does, because when I add everybody else up, 3 and 3 and 2 does not make 10. So the 7 is necessary. So 7 has veto power. And what about dummies? You should look at the 2 because that's the smallest. Is the 2 a dummy in this case? I see some people saying yes. Yeah, I think there is no way to make 10 by adding these numbers up in a way which uses the 2 in an important role, right? You could do 7 plus 2, but that's not enough. But if you did 7 plus 3 plus 2, that's 12, but then you don't need the 2, and so the 2 is not ever necessary. So 2 is a dummy. All right, and how about the last one there? 7, 3, and 2. So again, there's no dictator. Again, the 7 has veto power because you need to use the 7 in order to get to 10. Is it still true the 2 is a dummy here? I think it is. The 2 is still a dummy. Anything else to say about that one? I think actually there is something else to say about it. Is there anybody else who's a dummy, or perhaps anybody else who has veto power?
Doesn't the 3 have veto power?
Yeah, the 3 has veto power in this one also, right? So the 7 has veto power, also the 3. You need the 3 in order to get to the quota. In this example, actually, I would say, even though it's not obvious by looking at the numbers, actually, when you think about it, you realize the 7 and the 3 have equal power in this system, and the 2 has no power, right? Even though it seems like the 7 should have a lot more than the 3 and the 2. The 2 has no power at all. The 7 and the 3 have equal power, sort of 50-50 between the 7 and the 3. All right? Excellent. I hope that makes some sense. So we got 12 minutes remaining today. I can give you a little introduction to where we're going with this. We would like a real kind of measurement of the proportions of the power. We want a good way to measure the proportions of power here. Like, for example, that one that we just talked about, 10, 7, 3, 2, right? If we look at who's got the real power, where does the power lie in the system? Here, the power breaks down like the 7 has sort of 50% of the deciding power. The 3 has 50% of the deciding power, and the 2 has 0%. All right, this is the kind of measurement that I want to eventually talk about. Can you look at these numbers and somehow figure these numbers out? I mean, like purely mathematically, not in a way like you can kind of figure it out by thinking a lot about, okay, I got to add these up. But I mean, is there some kind of like formula? I'll say it's not really a formula, but I want to talk about some kind of real systematic way to take these numbers and figure out these numbers, which are really the important ones. These are the numbers that anybody in the real world would care about. The 7, the 3, and the 2 individually as specific numbers are not so important. to the way that the system is going to work in the real world. All right? Actually, there are two ways of doing this, and there are two ways which give you two different answers, and neither one of them is really the best. They're just two different ways of measuring the power. So let me just say there's no one specific way to do this. This is kind of a part of the character of mathematics as it exists in the real world that I think a lot of people are misled about because of like traumatic experiences as children learning math. Most of mathematics that is used in the real world does not have like a correct answer. Sometimes people tell me, sometimes people tell me like, yeah, I really like math because I always know when I'm doing math that there's a right answer, and I just have to figure it out. And maybe sometimes I mess it up. I don't get the right answer always, but it's like comforting deep down inside my heart to know that there is a true and right answer that I could get if I do it all right. If you feel that way, I'm not going to yuck your yum about that, but I would say like mathematicians and people who use math, sophisticated mathematics in the real world recognize that there is not usually a specific answer or a best way to analyze a problem mathematically. There are usually many different ways you could do it, and you hope that those answers will be useful in like making useful decisions in the real world, but they're not really correct in any kind of ultimate sense. So there's no specific way to do this measurement. We're going to talk about two strategies for measuring power in a system like this. We'll talk about two ways to do it, which will give you different answers. Although in this particular example, they will both give you this same answer, because this is a very clear-cut example. The 7 and 3 have equal power, and the 2 has no power. But in more complicated cases, the power is going to be analyzed slightly differently, and you will expect to get slightly different answers. So anyway, we'll talk about two ways to do it. And unfortunately, they are both named after people, which can make it hard to remember which one is which, but that's just how it is. So the first one, I'll give you a little introduction. We've only got 7 minutes left, so we're not really going to get into the details. Let me just say, before I say this, I don't have to write that word. Both are easy, but take some time. So this is not like a big formula that you're going to plug all the numbers into and like type into your calculator. It's easy to do them. This is something you could easily teach a kid to do this, although they will probably not want to do it, and maybe you won't want to do it. It's a bit of, you got to work it out, unfortunately, but it's not all that complicated. The first one, like I said, they're both named after people. The first one is named after two people. It's called the Shapley, Shubik. Those are the two names, Shapley and Shubik. The Shapley-Shubik power index. And it is a specific way of looking at a weighted voting system and figuring out how much power. And the answer that you get when you do the Shapley-Shubik is like a fraction. So in this example here, if you did the Shapley-Shubik, these answers would have been the 7 has 1/2 of the power, the 3 has 1/2 of the power, and the 2 has 0.0 of the power, right? So the answer is we end up with fractions, which you can convert into percentages if you want to, describing the power. All right. Like I said, there's two different ways to do this, which should suggest that you have to kind of make a decision about how exactly you're going to measure the power. And there is no one way to make that decision. There are different ways that you could make it. But the way that the Shapley-Shubik measures power, somehow we end up considering all the different ways those numbers could add up. And sometimes they could meet the quota, sometimes they could not meet the quota. What we're going to do is we're going to measure how often each voter, I'll put this in quotes, casts the deciding vote. All right. A dummy will never cast the deciding vote. That is because whether they vote or not, it never matters. A dictator, whenever they cast their vote, that will automatically be the deciding vote. For everybody else, maybe sometimes they're the decider, sometimes they're not. This is the kind of thing that we're going to look at with the Shapley Shubik. Can I tell you a traumatic story from my childhood about the deciding vote? This is minimally traumatic, but I still remember it. I was on like a little league baseball team, and I was never good at baseball. But there was one game when I scored a run sort of early in the game, and then later on in the game was tied, and my coach was like, "We really gotta win this game. I'm gonna, one of you guys is gonna be the hero when you score the winning run." And as it happened, somebody, we won the game because somebody on my team scored the winning run. Like they got a run after we had been tied. And my mentality was, I scored a run earlier in the game. Why is that guy the hero? Because he scored. Like I also scored, right? I was sort of objecting to this idea of measuring power by this kind of deciding vote. Like really, there is no such thing as one run which wins the game as opposed to another run which didn't win the game. Actually, like they both won the game. They both contributed to the game being won, right? This is my traumatic childhood story. But it is a fact that this is one way that you can think about judging the power. It's not the only way, and if you asked me as a kid, I would have said this is not even a particularly good way. But it works pretty well to analyze the issue of power in a weighted voting system. So we'll do the details next time. I think that'll do for now. See you tomorrow. Check out the homework.